Our planet Earth, a magnificent sphere of life and beauty, is far from static. Beneath its surface lies a dynamic and ever-evolving system of tectonic plates, constantly shifting and interacting. These plates, gigantic slabs of Earth's lithosphere, move slowly but relentlessly, driven by the immense heat emanating from the planet's core. This continuous movement is the driving force behind the creation of mountains, the opening of oceans, and, unfortunately, the occurrence of natural hazards like earthquakes and volcanic eruptions. These tectonic events, while potentially devastating, are a testament to the immense power of nature and the constant reshaping of our planet. Understanding these hazards is crucial for mitigating their impact on human lives and infrastructure. By delving into the science behind earthquakes and volcanoes, we can better prepare for their fury and coexist with the awesome power of our planet. Earthquakes, the sudden and violent shaking of the ground, are a stark reminder of the immense energy stored within Earth's crust. These natural phenomena can strike without warning, leaving devastation in their wake. The sheer power of an earthquake can topple buildings, fracture roads, and alter landscapes in a matter of seconds. These tremors originate from the boundaries of tectonic plates, where these massive slabs of rock grind against each other. The Earth's crust is divided into several tectonic plates that float atop the semi-fluid asthenosphere. As these plates move, they interact in various ways, sometimes colliding, pulling apart, or sliding past one another. The constant push and pull between these plates generate tremendous stress, and when this stress exceeds the strength of the rocks, it is released in a sudden burst of energy. This energy release is what we experience as an earthquake. Over time, the stress builds up as the plates continue to move, and eventually something has to give. This energy radiates outward from the point of rupture, known as the focus or hypocenter, in the form of seismic waves. These waves are akin to ripples spreading out from a stone thrown into a pond, but on a much larger and more destructive scale. These waves travel through the Earth's interior and along its surface, causing the ground to shake and tremble. There are different types of seismic waves, including primary waves, P waves, secondary waves, S waves, and surface waves, each moving at different speeds and causing varying degrees of shaking. The point on Earth's surface directly above the focus is called the epicenter, and it's often the area that experiences the most intense shaking. The closer you are to the epicenter, the stronger the shaking you will feel. The intensity and destructive power of an earthquake depend on several factors, including the depth of the focus, which can influence how much energy reaches the surface. The amount of energy released, which is measured on the Richter scale or moment magnitude scale. Larger energy releases result in more powerful earthquakes. The distance from the epicenter, as the shaking intensity decreases with distance. Areas farther from the epicenter may still feel the quake, but with less force, and the local geological conditions. Soft soils can amplify seismic waves, leading to more severe shaking, while bedrock can dampen the waves. Understanding these factors is crucial for assessing earthquake risks and preparing for future events. The power of an earthquake is measured using a logarithmic scale called the Richter scale. This scale, developed in 1935 by Charles F. Richter, has become a fundamental tool in seismology, allowing scientists to quantify the size of earthquakes in a consistent manner. Each whole number increase on this scale represents a 10-fold increase in the amplitude of seismic waves and a 32-fold increase in energy release. This means that an earthquake with a magnitude of 6.0 releases 32 times more energy than one with a magnitude of 5.0 and 1,024 times more energy than one with a magnitude of 4.0. An earthquake measuring 5.0 on the Richter scale, for instance, releases 32 times more energy than a 4.0 earthquake. This exponential increase in energy release explains why even a small increase in magnitude can result in significantly more damage and destruction. To illustrate the devastating power of earthquakes, let's consider two significant events: the 2004 Sumatra Andaman earthquake and the 1989 Loma Prieta earthquake. These events, though differing in magnitude and impact, both highlight the destructive potential of seismic activity The 2004 Sumatra Andaman earthquake, with a staggering magnitude of 9.1 to 9.3, was one of the deadliest natural disasters in recorded history. The sheer scale of this earthquake was unprecedented, causing widespread devastation across multiple countries. This megathrust earthquake, triggered by the subduction of the Indian plate under the Burma plate, generated a tsunami that ravaged coastlines across the Indian Ocean, claiming over 230,000 lives. The force of the tsunami was so powerful that it reached as far as the east coast of Africa, thousands of miles away from the epicenter. In contrast, the 1989 Loma Prieta earthquake, which struck the San Francisco Bay Area, had a magnitude of 6.9. Although smaller in magnitude compared to the Sumatra Andaman earthquake, it still caused significant disruption and damage. While considerably smaller in magnitude than the Sumatra Andaman quake, it caused significant damage to infrastructure, including the collapse of a section of the Bay Bridge and the Cyprus Freeway, resulting in 63 fatalities. The Loma Prieta earthquake also highlighted the vulnerability of urban areas to seismic events, prompting changes in building codes and emergency preparedness. These examples underscore the immense power of earthquakes and the importance of understanding their potential impact. By studying past events and improving our knowledge of seismic activity, we can better prepare for future earthquakes, mitigate their effects, and ultimately save lives. The science of seismology continues to evolve, providing us with valuable insights into the dynamic nature of our planet. Section 4. Volcanoes, fiery mountains of the Earth. Volcanoes, those majestic mountains that often dominate the landscape, are another awe-inspiring manifestation of Earth's internal heat. These geological formations serve as vents or fissures in Earth's crust, allowing molten rock, ash and gases to escape from the planet's interior. This molten rock, known as magma when beneath the surface and lava when erupted, originates from Earth's mantle, the layer beneath the crust. Volcanic eruptions occur when pressure from the buildup of magma within the Earth's crust overcomes the strength of the surrounding rocks, forcing the molten material to ascend and erupt onto the surface. The style and intensity of volcanic eruptions vary greatly depending on the composition of the magma, the amount of dissolved gases it contains, and the geometry of the volcanic vent. Some eruptions are explosive, sending plumes of ash and gas high into the atmosphere, while others are effusive, characterized by the relatively gentle outflow of lava. Section 5. Measuring volcanic fury, the Volcanic Explosivity Index. Understanding the sheer power and potential devastation of volcanic eruptions is crucial for both scientists and the general public. This is where the Volcanic Explosivity Index, or VEI, comes into play. To quantify the magnitude of volcanic eruptions, scientists use the Volcanic Explosivity Index, or VEI. This index is an essential tool in volcanology, providing a standardized way to compare the explosiveness of different eruptions across time and space. This logarithmic scale, ranging from 0 to 8, considers factors such as the volume of erupted material, the height of the eruption column, and the duration of the eruption. By analyzing these parameters, scientists can determine the relative explosivity of an eruption. Each whole number increase on the VEI represents a 10-fold increase in explosivity. For instance, a VEI of 3 is 10 times more explosive than a VEI of 2, and a VEI of 4 is 100 times more explosive than a VEI of 2. This exponential scale helps to illustrate the vast differences in eruption power. The 1991 eruption of Mount Pinatubo in the Philippines, a VEI 6 event, serves as a stark reminder of the devastating power of volcanoes. This eruption was one of the most significant volcanic events of the 20th century. This eruption, one of the largest of the 20th century, ejected a massive plume of ash and sulfur dioxide into the stratosphere, causing global temperatures to drop by about 0.5 degrees Celsius over the following year. The ash cloud from Mount Pinatubo circled the globe, affecting weather patterns and leading to cooler temperatures worldwide. In contrast, Kilauea, a volcano on the island of Hawaii, is known for its relatively gentle, effusive eruptions. Unlike the explosive eruptions of Mount Pinatubo, Kilauea's eruptions are more predictable and less violent. These eruptions, often characterized by slow-moving lava flows, create a mesmerizing yet dangerous spectacle. The lava flows can travel great distances, reshaping the landscape as they move. These eruptions, often characterized by slow-moving lava flows, are typically less explosive and pose fewer immediate dangers to human life. However, the slow advance of lava can be relentless and unstoppable, are typically less explosive and pose fewer immediate dangers to human life. However, they can still cause significant damage to property and infrastructure. The slow but steady advance of lava can engulf homes, roads, and other structures, leading to costly and sometimes irreparable damage. They can still cause significant damage to property and infrastructure. Understanding the different types of volcanic eruptions and their potential impacts is crucial for disaster preparedness and mitigation. The VEI provides a valuable framework for this understanding, helping scientists and authorities to better predict and respond to volcanic events.